Hello, welcome to this channel and thank you for coming to this class. In this video, I will talk about the second direct method to solve a system of linear equations called the LU decomposition. Don't forget to press like if you find this video useful and hit the subscribe button. Please also put in your comments down below and thank you very much for your support. Let's jump straight into the lesson today. Today we'll be talking about LU decomposition, and the two names that are related to this class will be Doolittle and Kraut. We will be looking at the two approaches, one being the Doolittle's approach, the other being the Kraut's approach, when we talk about LU decomposition. Now, when we talk about LU decomposition, what we are trying to do is to factorize a matrix. For example, we have this matrix here, a matrix A, 4, 3, minus 1, 5, 1, 3, 1, minus 1, 2. This is our matrix A. Now, previously in our Gaussian elimination class, we looked at how we can convert this matrix A into the echelon form, as you can see over here. This is the echelon form or the reduced form, after which we will be able to solve for the value of x, and then through back substitution, obtain the values of x2 and x1. Okay, so for today, we are going to look at another method to solve a system of linear equations, and it's going to take this form. So it's what we call an LU decomposition, L representing lower triangular matrix, while U denotes upper triangular matrix. Okay, so how do we go about obtaining the elements in the matrix L and the elements of matrix U? Let us have an overview of the three methods, including Gauss-Seidel, LU decomposition via Kraut's approach, and the LU decomposition via Doolittle's approach. So as you can see here, given the matrix A multiplied by the vector x, the unknown values of x, x1, x2, x3, equals a constant matrix here. So using Gauss-Seidel, we would obtain this echelon form. And using LU decomposition via the Kraut's method, what we get is two matrices, the product of which should give us the original matrix A. So what we can observe from here is that in the U matrix, the diagonal elements are all 1. Okay? In Kraut's method, that are the values we are going to use. Okay, while for the Doolittle's method, again, there are two matrices, the product of which will give you the matrix A as well. You can clearly see that the LU using the Kraut's method are different from the LU matrices that you obtain via the Doolittle's method. Okay, so we will see how we can obtain these two matrices, the L and U matrix, via the Kraut's method first, and then later on we will look at how we can obtain the two LU matrices obtained through the Doolittle's method. Okay, let's focus our attention now on the use of Kraut's approach to decompose a given matrix. Suppose we are given a matrix A. We would like to decompose it into the L and U. As you can see here, the lower triangular matrix is represented by this, while the upper triangular matrix is represented by this. So our job now is really to determine the values of all these elements. So how do we go about doing this? Well, one way is to do a matrix multiplication, of which you will get this. Now, we may do a comparison between the 3 by 3 of the original matrix with the 3 by 3 of this product of matrix multiplication. So that is actually quite useful. However, we will not be able to determine it right now unless we make an assumption. So this is where Kraut method comes in. Okay, in Kraut's approach, the idea is to assume the U11, U22, U23, all the diagonal elements as 1. So we will assume U11, U22, U23 as 1. Okay, so from the product of the matrix multiplication, you can see that if I substitute the UII, U11, U22, U33 as 1, you can simplify this into this. All right, so all this U11, U11, U11 will therefore be 1, and you will have this as a simplification. Now, by having this simplified form of A and equating that to the original matrix A, and simply by comparing the elements, we will be able to obtain some values immediately. Now let's do it in a systematic way. We will proceed in this fashion. We will do the first column to obtain the values of L11, L21, and L31, after which we will proceed in this horizontal manner to obtain, in this case, U12, since L11 is already known from our first round. And the next element that we can obtain will be the U13, because we would already have obtained the values of our L11. Okay, so let's do that. So immediately by comparison, we will be able to determine the value of L11, L21, and L31. And the values are as such by simply comparing to the original matrix A. Knowing these values, we will then be able to calculate for U21. And since this whole value has to be 2 and U11 is a 1, U12 will then be 2. Let's proceed on to obtain the values of U13. Okay, since L11 again is 1, U13 has to be 3 in order that when you multiply it, you will get 3. So let's proceed on to the second column. So for the second column here, L21, it's known from here. We know that's 3. And U12, we have just obtained it from here. So 3 times 2, that's 6. And that this summation has to add up to 5. So that will give us the value for L22, which is therefore a -1. Let's proceed on to look at this element here. Okay. Since L31 is known, that's 4, and U12 is 2, what will L32 be in order that the summation is 9? So L31 is 4, 4 times 2, that's 8. So 8 plus L32 equals 9. So L32 must be a 1. Now let's continue on. So for this case, the only unknown is U23. L21 is already known, that's 3. U13, it's 3 as well. So 3 times 3, that gives us 9. So this has got to be a -1 because we have to end up with an 8 since this is a 9. And L22, we have known that to be a -1. And therefore, U23 will have to be a 1. Okay, so when you sum that up, it must equal to 8. So there we have it, 2U3. And finally, the summation of this whole thing will be 10. So by just simple calculation, we can obtain L33, which gives us the value of -3. So now that we have all these values, we can then substitute back into our LU matrices. Okay, so individually we will populate all these elements, and that should give us these two matrices. Okay, so in this case, we have successfully decomposed the original matrix A into L and U matrices. Okay, as you can see here, for the U matrix, the diagonals are all 1 as we have assumed in this approach, the Kraut's approach. And the rest are all calculated and determined through this process systematically. So now that we have decomposed the matrix A into L and U, we can then later proceed to solve the system of linear equations for the unknown x1, x2, and x3. Now let's note one particular theorem here. Now, if Gaussian elimination can be used to solve the system of linear equation without row swapping or without row interchange, then LU decomposition can also be used. However, if Gaussian elimination cannot be used to solve the system of linear equation as a result of having a zero at the diagonal, in other words, you cannot proceed with Gaussian elimination without row interchange, as we have seen in the previous class. In that case, LU decomposition cannot be achieved as well. And why is that so? Now let's go back to one slide, right? Now you notice that in order to be able to find all these values, we really need to know the value of L11, okay? So if L11 is 0, you can see that it is not possible to determine U12, right? And if we do not if we are not able to obtain U12, subsequently we will not be able to obtain the rest of the other calculations. So in the same case here, when L11 is 0, U13 is also unknown. So that is a very simple reason why. If in the case where Gaussian elimination cannot be performed as a result of having a 0 at the diagonal, this same problem will also occur for LU decomposition. So let's proceed to solve the given system of linear equations, okay, using the LU decomposition method based on Kraut's approach. So this is the same system of equation as we saw just now. Okay, so converting it into the matrix format, it's the 1, 2, 3, 3, 5, 8, 4, 9, 10, which we decomposed it a few slides earlier. So we want to solve this system of linear equation, meaning that we're going to determine the values of x1, x2, and x3. So factorizing this matrix using the Kraut's approach, where the diagonals of the U matrix will be 1, assuming to be 1. That's our U. Okay. So we have decomposed this earlier. So we're going to solve for x1, 2, and 3. So how do we do this? Okay, so one step we can do is what we call the intermediate step. It's to replace this, to substitute this as Y, matrix Y. Let's try to solve this matrix Y first. So just copy and paste this whole matrix here. So nothing has changed, except that we are representing this part as vector Y. And we just copy and paste from here. So we can easily solve for y1, y2, and y3. So y1, immediately we know that's 16. And then forward substitute to y2. We will be able to, forward substitute in the second equation, we will be able to obtain the value of y2. And then subsequently, be able to solve for y3. So this is our values for y1, y2, y3. But this is not the solution, right? Don't forget that we're trying to solve for x1, x2, and x3. So since we have defined this part here as y, so let's do that. So you have matrix 1, 2, 3, 0, 1, 1, 0, 0, 1, multiplied by the matrix x 1, 2, 3 equals whatever answer we obtained here. So we can easily solve for x3, that would be 4. And through a process of back substitution, we will be able to obtain x2 and x1. And that's it. So this is the solution to the system of equation that we're given. And this is using the Kraut's approach of LU decomposition. Now let's take a look at a second example. So you are given a system of linear equation. First of all, let's write that in the format, in the matrix format. Now we would like to factorize this into the L and U. Let's again assume that the diagonals of the U matrix are 1, for the Kraut's approach. Doing a matrix multiplication, expanding out the L and U, it will look exactly like this. And by comparison with the original matrix A, this 3 by 3 matrix, straight away we will be able to obtain the value of L11, L21, and L31. And then using the same systematic manner of determining the other elements, we can then obtain U12, U13, and then subsequently U21, L22, U12, L32, and then lastly L33. Now I've already done the decomposition. You might like to check the values. So this is our L and this is our U. Notice that the diagonal of the U matrix are all 1 as we have assumed. This is the Kraut's approach. So again, to solve this, okay, so this is our matrix A. We would like to solve this. So let's start by doing the intermediate calculation. So we will define this part as the matrix Y, the unknown vector Y. Solving for Y will give us the values of 19, 5, and 5. And since we have already defined the values of Y as this, the product of this matrix A and the unknown vector X, we can then calculate for x3 immediately, which is 5, and then doing back substitution, obtain values of x2 and x1. And the answers are given here. Now this slide shows you the summary of the Gaussian elimination and the 2 types of LU decomposition. Okay, so we're going to look at the LU decomposition via Doolittle in this next segment. Now, let's say we're given a matrix A. As before, we have matrix A. We would like to decompose it into matrix L and U. It looks like this, L and U, as before. So when we do a matrix multiplication, you will get the 3 by 3 matrix. So nothing has changed compared to the Kraut's method. So in this Doolittle's approach, we would like to assume L11, L22, L33 as 1 instead of the diagonals of U. So we will assume the diagonals of L matrix as 1 in this case. Okay, so simplifying it, okay, we will get this. So this will be our product of multiplication between L and U, where the L11, L22, L33 have been assumed to be 1. So using this A, and by comparing it to the given matrix A, immediately we can obtain the values of U11, U12, and U13. Doing it systematically, doing horizontal, and then column, then second horizontal here, and then lastly for this element, we will be able to obtain the rest of the other elements. Now with some patience and practice and a high degree of care, you should be able to obtain all these values. Okay, so U11, U12, and U13 are simply 4, 3, and minus 1. Okay, then you go down in this manner where since we know U11 and the product of which has to be a 5, so L21 must be 125. Okay, and then finally for this, since U11 is a 4, L31 has to be 1 over 4, which is 0.25. So you can work that out slowly, and you should be able to obtain all the values given here. So matrix A can now be factorized into the L and U, in which case, in the Doolittle's approach, the diagonal line, the diagonal elements for the L matrix will all be 1, as you can see here. And all the other elements, we have just obtained them in our previous page. So we just simply substitute all the values that we have obtained and fully populate the L and U matrix. Okay, so in order to solve the system of linear equations, we can express it this way. So this is our L and U, which is the decomposition of matrix A, multiplied to the unknown vector X equals to the constant matrix here. So representing this as the Y vector, the unknown values of Y1, Y2, and Y3 can be obtained. First by knowing the values of Y1, which is minus 5.7, and then doing a forward substitute, we can obtain Y2 and then Y3. And again, this is not our final solution. This is simply the solution for Y1, Y2, Y3. And since we have defined the value of Y, okay, and these are just what we obtained earlier. So using the back substitution, we can obtain the values of X3, X2, and X1. And that's it. Now, in Doolittle's approach, there is actually another way to obtain the decomposition of the matrix A. And this is what we call the shortcut method by exploiting the results of the Gaussian elimination. Now, let's take a quick look at the result of the Doolittle's method, which we obtained earlier. We managed to decompose matrix A into L and U. And these are the two matrices that we obtained earlier. We went through quite a bit of calculation and quite a bit of patience just to obtain these two, right? However, if you look at the result of Gaussian elimination of the matrix A, you would recognize that the echelon form of this same system of linear equation looks like this, isn't it? Now, if you compare this to the U matrix, you can see that they are identical. So you can say that the product of the Gaussian elimination, the echelon form, can be used as the U matrix. They are the same, okay? What about this L matrix? Are we able to obtain some information from the Gaussian elimination result to be used to help us find the L matrix? Now, surprisingly, that if you recall during the process of getting into the echelon form in the Gaussian elimination, we had to determine certain fractions, certain ratios, all right? You also recall that for the first ratio, when we were trying to transform the given matrix A into the echelon form, the first ratio was 5/4. Okay, 5/4, it's actually 1.25. And the second ratio was 1/4, that was 0.25. And then the last ratio, where we try to obtain this, we try to make this number to 0, which resulted in 0. Okay, the ratio was 1.75/2.75. Okay, so you can see that these three numbers were actually obtained from as a result of trying to get to the echelon form in the Gaussian elimination process. Okay, so we can, in fact, these are the three numbers that goes into the value of L21, L31, and L32, right? So you can see that these numbers are identical. Okay, and since we know the diagonal elements are all 1, so we have fully populated the L and U very quickly simply by taking the information from the Gaussian elimination process. Now, this is certainly a much faster way to obtain our L and U. This will be very useful because once we are able to obtain the LU decomposition of a matrix A as a result of the Gaussian elimination, we will not need to repeat this process if the right-hand side of the equation changes, because the matrix A will remain the same, producing the same LU decomposition. And so, with this demonstration, we can see that in order to find the LU decomposition based on the Doolittle's method, by simply exploiting the GE results, we can easily obtain the L and U. And that's it. Well, thank you very much for joining me in this lesson and hope it has helped you. If you like this video and found this useful, please press like and hit the subscribe button for further lessons next week. I've put up a link to the Excel implementation at the top right-hand corner. See you there.